second section of the chapter 16. So this is a record in table 2 of the NBER, National Bureau of Economics, something like that. It records for every month whether the economy is in recession or whether it is in expansion. So it's a sequence of ones and zeros. Zero meaning it's in recession, and then one meaning it's in expansion. Now, obviously, you have a sequence of zeros showing the economy is in recession, and then it transits to expansion. So either it's positive or it's negative. It can't be both. So growth is either positive or negative. So if its growth is negative, then it's recession. If growth is positive, then it's expansion. So actually, I think it's not that simple. It's not growth positive or negative. There is a normal rate of growth which is assumed, and then if it's above normal rate, then it's called expansion. If it's below normal rate, then it is a recession. But for the statistics, this doesn't matter. We have a sequence of ones and zeros monthly, and now what we want to check is there are months in which the recession ends. If you have a sequence of zeros and then there is a 1, then the recession has ended on that month. So now the question being explored here is the probability of ending of a recession dependent on the month or not? So here we have a list of data. January, there was one end of recession, and total 44 times in the data set. January was a recession month, and in one of these months, recession ended. And February, we have the same thing. One recession ended, and 48 total recessions periods. And so we have a lot of different months. So now the question is this, in this, do we have any significant differences in months? So one way to do this, which we will try later, is to use the chi-squared test. But right now what I want to do is to look at the empirical Bayesian method to answer this question. Is there a difference in the months? So now what we have is that for each month there is a natural estimator of the probability that recession ends in January. And that is, in January you have one recession ended and there were 44 recessions. So for January, the natural estimator is 1 over 44. This is the probability of recession ending in January. In the next one, we have 1 over 48. Yes. February, it's 148, so 1 over 48. So these are the theta hat 1, theta hat 2. For each month, I have an estimator of the probability that the recession ended in that month. Now, one very important thing, this is the thing which makes empirical Bayes work. Basically, suppose that theta hat I, or IID, normal, with mean theta and variance VI, so the common mean. Then they will be all different. This is the thing, that automatically, even if they are coming from exactly the same distribution, they will all be different numbers. So if we start with a model which says that each theta hat I has its own mean, then we will get a confirmation of this, because we will estimate theta I by theta hat I. And so we will have all different estimators for each one. And this is not good. And we know that basically the random process scatters something which is same in a little bit, spreads it out. So this is why if we shrink, we will recover the true parameter. This is the secret of shrinking. That's why shrinkage actually works in the real world, unlike most econometric techniques that your friends are learning, full information, maximum likelihood, and method of moments. All of this is just garbage. But this is something which really works.
So what does 44 and 48 mean?
44 was the total number of month times in which January there was a recession. And in one of these Januaries, the recession ended in that month, in January. In February, there were 48 months in which there was a recession.
The number of Januaries for particular time period.
The number of Januaries in which there was a recession. So now we have all of these 12 different probability estimates, and we want to know, are they all coming from the same theta? So now there are two big ideas which are not written in the technical details which is given in the text. So I'm going to explain the two big. One of the big ideas is exactly this, that we need to shrink to get rid of this excess fluctuation. The randomness of the data automatically spreads out the true value. So that's one of them. And the other thing which is important here, which I haven't mentioned specifically, is that the sample size is now very small, because you have 1 out of 44. So you have basically, you see, binomial can be approximated by normal if n is large and p is not too small. Basically, a rule of thumb is that np should be equal to 5. So here with the p being 1 over 44 approximately, we don't know what the true p is, but maybe it's around 1 over 44, and the n being 45, so the np is around 1, which is very small. So that means that the normal approximation is not valid. So we cannot do, and this is the same is true in all your data sets. If you're a binomial, if the p is low, if the np is small, then the normal approximation will not work very well. And if it doesn't work very well, then the methodology for the normals will not work, but empirical Bayes will still work if you do the beta binomial, which is what is done here. I haven't emphasized this point in the write-up, but this is a very important point here. And in fact, it is interesting, because this actually was a paper that was published, and in this paper, because Geisels used a normal approximation, he came up with the result that there is a significant difference, and it is not significant if you do the right calculations. So by using asymptotic theory, he made a mistake, and this is unfortunately very common in econometrics, that people use asymptotic approximations when they are not valid, because well, that's the common practice. So these are the two major points which are not written. Now I would like to explain again not in a technical way, but in a more intuitive way, how we do this. So basically, so we want to assess, are all the thetas same? So we use the standard method. Okay, let's assume all the thetas are the same. Actually, then we have that the theta hat I minus theta squared. So I'm just providing a heuristic intuitive argument for you to understand. So let's assume that this theta is known. What we do is we will estimate this theta by taking a weighted average of the theta hat I as usual. And then since there are 12 of these, so our variance will be quite small. So let's just pretend that the theta is known. Then this theta hat minus theta squared, the expected value of this should equal Vi. This is true if all the thetas are the same. If they are not the same, then what we will have is that this will be theta hat I minus theta I plus theta I minus theta squared. And now it turns out that if you expand this, you will get theta hat I minus theta squared, which is the data variance of theta hat I around theta I, its own mean, and then the variance of theta I around the common mean of the thetas, which is the standard, empirical Bayes methodology, and the cross term will cancel. So this will be equal to Vi, which is the data variance, plus P, which is the prior variance. So now, if I take the sum of all of the deviations, so I take theta hat 1 minus theta squared plus theta hat 2 minus theta squared, and so on. So this is an estimate of V1, this is an estimate of V2, and so on, up to V12. All of them have their own variances. Then basically that's it. We compare this with the sum of the variances here. If this is significantly larger than this, then we know that there must be some P which is causing this difference. If this sum of squares is very similar to the sum of the variances, then we say that okay, there is no prior variance left. So that means that all of the fluctuation that we see is explained by the data variances. So there's nothing left for the prior to vary. So it's okay to assume that the thetas are the same. So this is the big picture. And in fact, it turns out in this case that exactly this is what the result that becomes out. Actually, what we were trying to do when we tried to, we started with this paper, Steve and I, long time ago, and we wanted to basically estimate all of the thetas separately using empirical Bayes. This is one thing which empirical Bayes is very good at. When you have, see, basically what happens, and this is a very common situation when you are applying empirical Bayes, that you have, and we will see it many times later in this collection of real-world examples. Here you see we have what is called a small sample, because you have one recession end in 45 periods. This is a small sample because n times p is only 1. Basically, the sample size is small or large depending on the p. For example, if p is 1/2, then 45 is a large sample. You can do normal approximation without any fear, no problem at all. But if p is 1/45, it's too small, and now normal approximation will not work. So p around 5/45 is where it starts to work barely, and one would be any better off avoiding it at 5. And now if p is 10/45, 25%, now we are safe. And if you have a n equals 45, then you can use large sample approximations without any fear. So here we have a small sample situation. So now in small samples, the estimates, all estimates are poor. So you're going to get your theta hat 1 from a small sample is going to have variance. All of these different estimators are going to have their variances. Now what the Bayesian estimator does is that it borrows strength from the other data. I have January data, but I also have February data. Now February data is not directly related to January data, especially in this context, but if all of the data is coming from similar mean, and here this assumption is very plausible that the theta i's are similar across months. See, this is because of the you have to know the real world context. In some situations we can think of there would be no connection between theta hat 1 and theta hat 2, and then you cannot borrow strength from that. But here we can. It is reasonable to think that the probability of ending recession in January and the probability of ending a recession in February are similar if they are not the same. So that's all that we need for the empirical Bayes process to work. And as long as they are similar, then you see, if for example if we were completely missing data for January, then what would we do? We'd say, okay, let's use the data for February, because nobody would object to this, and that means that it is a reasonable thing to do. So basically what the empirical Bayes does in a small sample, it borrows strength from the other data which is similar, and it's quite clever about this in the sense that we will see in the formula that there are two components. Basically there is the prior variance and the VI, and these are compared. If there is a lot of if the data variance is very low, so we have a precise estimate, then you ignore the prior and you say, okay, I'll just use my own data because I have a lot of it. If the data variance is large, you have a very small sample, and then you say, okay, let's use the prior. So this same kind of situation arises in your panel data modeling, where you're doing constant coefficients, random coefficients, etc., where you have two options. Either you can set them all the same, or you can allow them all to be different. Both of those are bad options, because setting them all the same doesn't allow for diversity, and leaving them all separate creates a problem that you get very small samples for each of them. So the empirical Bayes is an optimal compromise between these two. It also combines the data, but it also keeps them separate, and it does this in a way that is the data tells it to do. And the data tells you, if there is a lot of diversity, that okay, keep everything separate because there is not enough match. The prior variance is large. That means that each data is separately estimated. If the prior variance is low, and that's something you estimate from the data, that means that the remaining data is providing good information, so you can use the other data to estimate in your small sample. So this is why the empirical Bayes method works very well in the right context. Now there are some contexts where it doesn't work very well. If you have large samples in each subsection, then the empirical Bayes doesn't help, because each section is already accurately estimated, so the prior information doesn't add. So, but if you have small samples in each part, but large sample as a whole, then this is a situation where empirical Bayes has a potential to produce very good results. All right, now that is the big picture. Now we look at the specific details. So first thing is that in this problem we have to use the beta binomial procedure, because we cannot because this is a small sample, so we can't use the normal approximation. So what we do is we set up the densities which are binomial densities. So we have these random variables Ri, Now, one thing that I want to tell you people is that this material that I am teaching you is, even though this book was written in '96, very few people understand the empirical based methodology and procedure. So there is a lot of room and scope for applying this. And the other thing is that you learn something only by doing it. So I'm going to go over this material only roughly, but you will have to, if you want to acquire mastery of this, then you will have to work through it yourself on your own and try to understand what it's saying. Allah Ta'ala says, وَالَّذِينَ جَاهَدُوا فِينَا لَنَهْدِيَنَّهُمْ سُبُلَنَا. So Allah Ta'ala gives guidance to those who struggle for it. So basically struggle is tied to guidance. So very often any students come to me and say, okay, I want to solve this problem. So I say, well, if I solve this problem, then I will learn how to solve it, but you will not. So if you solve the problem, then you will learn how to solve it. And that's how it works actually. Now, of course, there is a balance. There is a challenge level which is too low. If I make the problem too easy, you won't learn anything. If I make it too hard, you will become frustrated that, oh, I can't do it. And this is beyond my capabilities and so on. Nothing is beyond your capabilities, but students are weak. So they are easily frustrated and they give up too easily. Actually, this is one of the secrets of success, is to just try again. This is the people who succeed are the ones who just keep plugging at it. 10 times. I told you that in my thesis there was 100 pages, but I wrote at least 2,000 pages. So this is only 20 pages of work for 1 page of output is common. When I was taking my first year statistics course, Bradley Efron was teaching us the graduate course in PhD statistics, and every week he would give us an assignment, and the assignment would be just unbelievable. So we would have to look in the library. There was no relation between what he assigned us and what the lecture. So we would study here and there and look up books, and a few weeks later he asked us, okay, how much time are you spending on solving these assignments? So on the average, students were spending about 20 hours for the assignment. So, and this was just one course. And I was taking
20 hours
Kya
a
hua?
week.
20 hours a week, exactly, for one assignment, yes, for solving the assignment. And I was taking 5 courses. I was taking the PhD courses, the comprehensives in economics. There were 2, micro and macro, and then there was in statistics. There was a statistics sequence and a probability sequence. And I was also taking the math graduate course because so I had a tough time. But I was also spending around 17, 18 hours, which is on this stats assignment. So basically you have to work. If you want to learn something, you have to work. And the only thing that I want to tell you is that it is rewarding. This is the problem. This is the issue, that students are ready to work, but they don't want to work if you work a lot and you get nothing for it. So there is something that you will learn, and it is very worthwhile. And every day I try to learn at least one thing new, and it requires everyday work. And has a basically the secret to success is to set a very large goal, a big vision, and then work on it one step at a time. A very famous incident, I think Abu Hurairah radhiyallahu ta'ala anhu said to one of his friends that let us go and learn some hadiths from people. There are lots of people around and they are getting older, and
they will all die out and we will not have these sources. So he said, no, we are just little itty-bitty people, and there are very big ulama with lots and mountains of hadith. How can we possibly achieve any match to them? So he didn't try. Abu Hurairah went, and every day he would learn a little bit. And eventually, the time came when people started coming to him to ask him questions. And so his friend said, oh, I made a mistake, and I didn't realize this. So basically, everything happens one step at a time. If you set a large goal, but you don't let the large goal daunt you that, okay, this is so far, how can we reach? So you just take one step towards the journey of 1,000 miles begins with a single step. So right now, actually, what I am doing is that the whole of econometrics that we have is complete garbage, nothing worthwhile in it. But there is a way to do things correctly. So if you start working, you can be the leaders of the world in statistics and econometrics. But you have to work. You cannot become leader just by sitting and listening to lectures. You have to do your own work. Alright, so the situation that we have is that we have Ri is the random variable. This is the number of recessions which end. And now Ri will be binomial with parameter theta I and Ni. So Ni in January is 45. Theta I we don't know. The observed value of Ri, the number of recessions which ended, was 1. Right? And similarly we have for all of these. These are our binomial random variables. And now, so the distribution of this is theta I to the Ri, 1 minus theta I to the Ni minus Ri. So that's the density for the one of them, and then we have, there are 12 months, and there are some constants. Let me put it down. Ni, Ri, although it doesn't matter. Now, so this is the joint density of the theta I. Now each theta I has a prior density. This is actually the density of theta I conditional on. Oh, sorry. This is the density of Ri conditional on theta I, and then we will multiply this by the density of theta I conditional on the common mean theta. What I am calling theta I is written as Pi in the notes. And so there is no theta here. That's the common mean is used in the normal distribution. Here we just have a common beta density, which is gamma of alpha plus beta over gamma of alpha, gamma of beta, and then we have theta I to the alpha minus 1, 1 minus theta I to the beta minus 1. So this is the joint density of all of the theta i's and all of the data R1 through R12 and theta 1 to theta 12. Now, in the standard empirical Bayes methodology, we want to convert this into the posterior density, and that's trivial. Yeah, that's the important thing about the Bayesian methodology. Just ignore the constants and write down the density product I equals 1 to n, 1 to 12,
theta I to the Ri, this comes from the data, plus alpha minus 1, this comes from the prior, and then we have 1 minus theta I to the Ni minus Ri plus beta minus 1. That's called the kernel of the posterior density. This is all of the terms which involve theta, and so this kernel, the only thing we need to do to make this a density is to supply the constant which will make it integrate to 1. And that's trivial because this is in the form of a beta density, so all I need to do is to put in gamma of the sum of these two, which will be gamma of alpha plus beta plus Ni, and divided by gamma of Ri plus alpha, gamma of Ni minus Ri plus beta. Right? So that is the posterior density of the thetas. These are okay, so that's the
ऐड करने की टेक्निक है जो भी आप बोल रहे हैं, हमने कांस्टेंट इस तरह से ऐड करना.
Right. देखो, I'm ignoring the constant, but we can all keep track of all of them. So ये इसको निकाल लो, take this out, then we supply the constant here and multiply by the reciprocal of this constant, and that part which comes over here, that's the marginal density of the data. This is the density of the theta I given Ri, and then there is the marginal density of Ri, which is left, which I have ignored. And if you keep track of the constants, then you can get the marginal density of Ri. Okay, so what happens next? Okay, so now the next thing that we need to do to get our empirical Bayes estimators is to estimate the alpha and the beta, which are the prior parameters. And how do we do that? Well, there are two parameters, alpha and beta. Now the interesting thing about, so this is what makes this problem different from the normal, because the formulas are different, but what we are doing is the same thing, but because it's beta binomial, the formulas are different. So you have to understand, this is very important, that the concept is the same, the practical details are different. You have to keep when you're working at the higher level, understanding what is going on is not just in the formulas, but at the conceptual level, nothing has changed. This is exactly the same problem as the normal, but in the practical detail level, it is different. So you have to keep this is basically any mathematical thinking involves two levels of thinking. The higher level is the understanding what is going on, and the lower level, which is what people learn, is to memorize these formulas and have no understanding of what is going on. Then that's not useful. Not useful. Okay. So now the thing is that in the beta density, the expected value is alpha over alpha plus beta. Yes. If you have a beta density with the parameters alpha and beta, then the expected value of x is alpha over alpha plus beta. So what we have is that the expected value of theta I given Ri is equal to, now the posterior density, the alpha and beta are here. The alpha is Ri plus alpha, and the beta is Ni minus Ri plus beta. So in the numerator you have Ri plus alpha, and in the denominator you have the sum of these two. So Ri cancels with the Ri here, and you get Ni plus alpha plus beta. So the posterior mean of theta I is Ri plus alpha over Ni plus alpha plus beta. Notice that
this is quite similar to our original maximum likelihood estimators. If I put 0 for alpha and 0 for beta, then I will get Ri over Ni, which is the conventional estimator for theta I. Now 0 and 0 are not very good values for theta and for alpha and beta. They're not very useful values, and that's why the conventional estimator doesn't perform very well, because it has a tendency to take extreme values. This alpha and alpha beta smooths out the estimator. It makes it stay away from the edges of 0 and 1. And what are the right values? Well, when you have no information, then alpha equals 1 and beta equals 1 are the right values, because that makes the prior uniform. All the thetas are equal. Alpha equals 1, alpha minus 1 becomes 0, and beta minus 1 becomes 0, so you have exactly a constant flat density. Now it's possible to define mu naught equals alpha over alpha plus beta. This is the mean of the prior. The prior, remember, theta I, all of the theta have the same prior. It's beta with alpha and beta parameters. So the mean of that prior density is alpha over alpha plus beta. That is the prior mean. And that is where we are going to be shrinking everything towards. So that's the prior mean. And you can now, I have done the calculation, show that this number, this posterior mean, is a weighted average of Ri over Ni, which is the theta hat I, and mu naught. In fact, so mu naught is this thing, and theta hat I is Ri over Ni, which is the standard conventional estimator. And the weight set, this is exactly a precision weighted average. So exactly like the normal distribution, but this requires some algebra, which is done in the notes. And but basically, so conceptually, there is no difference. We are just taking a weighted average of the prior mean and the data mean. We need to do, instead of, there are two ways to proceed. And we can, what we can do, what I do here, there are actually many ways. I mean, what we want to do is estimate alpha and beta. That's the goal. These are the prior parameters. So empirical Bayes always proceeds in this way, that you use the data to estimate the prior. This is not a very good method, actually. I mean, the correct method is to do hierarchical Bayes, which is much more complicated, and we will get to that later. But first, actually, it's very useful to understand the empirical Bayes method, because this is intuitively easy to understand. Hierarchical Bayes becomes very difficult. It's a third level. So here we are working with second level understanding, and once you acquire that, then it's possible to step on that higher ladder and get to the third level understanding. Okay, so now there are many ways. Okay, so what happens is that the part that I didn't write down, the marginal distribution of Ri, it is written down in the notes. This marginal distribution does not have any thetas in it, because we took the theta i's out of the theta. So there is a conditional distribution of the theta I given alpha and beta. Sorry, no, this is not given. This is given R times the marginal distribution of the R's. Now this marginal distribution does not depend on theta. It depends only on alpha and beta. So now, how will we estimate alpha and beta from the marginal distribution? This is the issue. Now there are many ways to do this estimation. One way is the method of moments, which is what I actually use. So the method of moments says that look at the expected value of these densities. All of them have common mean alpha over alpha plus beta. All of the Ri's have the same mean, because the mean of Ri is theta I, and the mean of theta I is alpha over alpha plus beta. So in the same way as in the normal distribution, the middle disappears and you get to the... So then it's easy. I have theta hat I is an estimator of this data mean, so Ri over Ni. So I just average them all. This is the method of moments estimator. I can be more sophisticated if I want to, and I can use a precision weighted average. That it turns out doesn't matter very much because the fluctuation in the variance is not very large, but so minor differences. But anyway, so that gives us the mean. Now the second part is how to estimate the variance. Now, as I explained, that I was actually trying to estimate alpha and beta in order to get my estimators, and now different methods. I used the maximum likelihood method. I said, okay, let's fix this value, alpha over alpha plus beta, and then I have this likelihood function which is written down explicitly, so I can just maximize. So I set the I did it two ways. I set the computer to maximize, didn't give me any answer. I tried to do it analytically. Again, there was no point at which the derivative is zero, so I was a bit surprised. I said, what's happening? Then I analyzed this problem, and I realized that what's happening is that the variance, the prior variance, is going to zero, which is, I think, the same as beta going to infinity, if I remember correctly. So as you increase the beta, you decrease the variance. The more you increase the beta, the better the fit. So basically then what happens is that the data is telling you that the prior precision is very high. And what does that mean? It means that the prior precision is high, variance is low. It means that basically you should use the prior mean and not the data mean. It means that the model that we are coming up with is that all the thetas are the same. If all the thetas are exactly the same, see, if theta 1 equals theta 2 equals theta 12, they are all the same, then basically this is the saying that they are normal with the common mean and variance 0. So what the data is telling me is that all of the months have exactly the same probability of ending recession, which is quite standard and expected and normal. This is what we would expect in this situation. So basically right. So we find that what the main finding of Geisel's was that the thetas are different is wrong. Now, so the estimated, the Bayesian and the empirical Bayes estimates are just that all of the theta hat i's are the same. And how to estimate? Well, we just combine all of the data. Suppose that there is no months, then we have so we just have 1 in January. We just add up all of the recession endings, and that gives some number, and we add up all of the total recessions, and that gives some, and we take the derivative. Now this time, when we combine all of the data, it becomes a large sample, and now we have a large sample estimate. So we don't need to worry about the Bayesian estimator anymore. The ratio of the number of endings to the total number of recessions is a reasonably good estimator of the prior mean. And
that is the common probability for all of the months. And that's it. There's no further. So now there's one more question. Why did Geisels find that the things are different? That was a puzzle to us when we did this. Because actually we started by assuming that his result was right, and so we were going to get different estimates for each month. And when we found out that this was not true, then we said, okay, now we have a contradiction, a conflict between what I have found and what he is. He's saying that the months have different probabilities. I'm saying they're all the same. So now, why did he get different result and why did I get a different result? So basically, then what we do is we look at the chi-squared statistic, summation theta hat I minus theta bar squared. So this would be a chi-squared with 11 degrees of freedom if the sample size are large. I'm not sure that this is correct. Anyway, there is a way to. Oh yes. There is a test for equality of means. I don't know if you have. In a normal distribution theory, you have a test for equality of means. This is done by a chi-squared test. There are different ways to set it up. But anyway, what happens is that when you carry out this test, you get a statistic which is significant and which rejects the null hypothesis of equality. But this happens because of the normal approximation. The normal approximation is not valid, so there is a further approximation that the chi-squared approximation is also not valid. So you get a significant statistic which is not correct. If you do the same statistic and you assess its significance using the correct distributions, then you find that this result is not true. This value of statistic is not significant. To the section 3, this is again a real example. So you have a real world problem. You are sitting in Bronx. This is actually where it was done. The study was carried out, and in a fire station, and you get a fire alarm. There, people sound. So there are 216 different districts, small areas, 245 areas. Each area has many buildings. Every building has a fire alarm installed in it. And so now you have a box from which the alarm is coming, and you have a box history. In the box history you have that this alarm in the past year or past 10 years was sounded, we got an alarm from this 10 times or 20 times, and out of those there was a genuine fire in 3 times or 5 times or whatever. So exactly the same as this recession ending and stuff. You have a NI, which is the total number of times that the alarm sounded, and then real fire or big fire. Something which requires a genuine response. So if this is 20 and this is 5, then you have the probability, a simple estimate of the probability that there is a fire is 5/20 based on the box history. Now, now the thing is that what you want to do is that if it is the optimal, the correct decision that you need to make is that you have a whole collection of fire trucks, and either you can make an all-out response, send send everybody out to investigate. If this is a big fire, then this is the right thing to do. And if it is a false alarm, then this is the wrong thing to do. Not only does it incur extra costs, but also there is a chance that a genuine fire alarm will come in while all the trucks are gone, and then you will be stuck with the problem. So you want to take some action. So basically the right algorithm is to say that, okay, there's some critical value P star. If the probability of a genuine fire, we estimate P hat I, and if it is greater than or equal to this, then we make an all-out response. And if it is less than this, then we send one truck out to investigate. So this is something which is called a bang-bang solution. In some situations, the optimal solution, you probably have studied it if you have done optimal control. This is studied in economics anyway. That in some problems, the optimal solution involves either is of a 0-1 type, and this is one of these situations where if there is a fire, you send an all-out response, and if there is none, you send just one truck. It's not, the solution is not continuous in that as the probability increases, you increase the number of trucks. This is one thing that intuition might suggest, but actually when you solve the mathematics, it turns out that this is the right solution. It's called a bang-bang solution. Either you do the all or nothing type solution. So this turns out to be the optimal response, but that part doesn't have to do with the statistics of the situation. So we just say, okay, this is the procedure. Now the only thing is to estimate P hat I. So now what happens is that if you what if there is no box history, or what if the box history is very small? So we only had about 3 alarms, and there was no response on any of them. I mean, none of them were big fires. Or if we have 0 NI, there's no box history. This kind of thing can also happen. So what should we do? Well, the standard thing to do was that there were 245 different areas within and these were all neighborhoods, maybe one block. So there are lots of blocks, 245 different blocks. Inside each block there are 50 buildings or something like that. So we have an estimate for each neighborhood. So for each neighborhood, we can look at all of the boxes within that neighborhood and all of the alarms sent. So now we have something. That's sufficiently big area that there will be a history for that area, and there will be alarms and there will be responses, and we can do fairly good estimate of the area probability. So now obviously if you have 0, if you have a box which has 0 history, then the right thing to do is to substitute the area value, the P hat I. So this is again exactly the same structure as the empirical Bayes that we have been discussing. That now if the box history is very large, if you have a lot of history in the box, then you have a very reliable estimator for that box, so you don't need to use the area history. So this is exactly the setup in which the box history works. And this is again a binomial model. And so we have P hat I. This can also be done by beta binomial methods. But now I'm going to try to show you the normal method. Even though this is, again, a small sample, so the normal approximation is not good. But there is a way to fix that problem. P hat I is normal with mean Pi and variance Pi times 1 minus Pi over Ni. So if I'm going to approximate a binomial by a normal, then this is the approximation that we will get. Now it turns out that there is a way to make this normal approximation work fairly well, and that's called the variance stabilizing transformation. And if you take xi, xi equals 2 arc sine p hat I square root of this. Hecto to hogi isme. Then it turns out that this is equal to, this has normal distribution with mean 2 arc sine square root of pi and variance equal to 1 over Ni. So the Pi over 1 minus Pi comes out of the, this is why it's variance stabilizing, because the unknown Pi, which fluctuates a lot, is taken out of the variances. So the variance becomes now much more stable. See, with when the Pi is in the variance, then you get the problem that you have to estimate the variance, and Pi itself is very, I mean, the whole problem is that the Pi's we are estimating are very unstable, unreliable. So we get a double problem, that the mean is also unstable and the variance is also unstable, so the estimates become unstable. So this variance stabilizing problem transform fixes the problem to some extent. Basically what happens in this variance stabilizing transformation, we've already discussed this in the first time, and at some point you should go over this, although it's not a big deal. That basically what happens is that you can make a Taylor series expansion of this, and basically the second order and higher terms will be small because p hat I tends to be close to Pi. So the expansion will be in terms of p hat I minus Pi. So this is called a stochastic expansion, and is a very advanced technique, but it's actually quite simple. So anyway, the thing is that here, by using this transformation, we can work within the normal framework, which we already know how to do. So now what we have is that, okay, so all of these have, so basically what we can write is that xi is normal with mean theta I and variance di. This is the structure of the problem. Theta I is 2 arc sine square root of pi, but that doesn't matter. It's just theta I. And di is 1 over ni. So yes?
The arc sine kya hai?
Arc sine kya hai? Sine is theta, is the inverse of the sine function. Yes. X is equal to sine theta. Arc sine of x is equal to theta. So you can calculate it from the sine.
सर इसकी ट्रांसफॉर्मेशन वो दूसरे जरिए से नहीं हो सकती कि हम इसकी स्टैंडर्ड डेविएशन को उस पर डिवाइड करें?
क्या मतलब?
तो वेरिएंस जो होता है उसका वो स्टेबल हो जाता है।
नहीं मैं समझा।
सर अगर हमारे पास ऑब्जर्वेशन से हमने उनका वेरिएंस लिया और वेरिएंस के बाद जो हमने
ये है वेरिएंस pi times 1 minus pi over n है।
इसकी स्टैंडर्ड डेविएशन बनाई और ऑब्जर्वेशन
इसको स्क्वायर रूट लेंगे तो स्टैंडर्ड
और डिवाइड कर दिया नीचे।
So the thing is that pi is unknown. If pi was known, then we could do it. But if pi is unknown, we can't do it. And just like in GLS, if you say, okay, let's estimate the pi and divide, then you get very erratic estimates because there is a lot of noise in the pi. So the whole idea of the variance stabilizing is to get rid of those pi's without having to estimate them. All right, now this is set up in the way that we can that it can be used that we can use our standard empirical Bayes methodology. And so basically you have theta hat I is normal with mean theta I di, and the theta i's have common mean and common prior variance P. Now the posterior estimator the Bayesian estimator theta at B is going to be precision weighted, so it's 1 over di this precision is going to apply to the data estimate so it's a weighted average of the data mean, which is the box estimate, and this is the prior estimate and the prior estimate will be the region estimate or the neighborhood. So the neighborhood estimate comes from taking all of the boxes in all of that neighborhood and combining them to get. So what was the standard practice before Rolfe and Carter studied this method in Branch actually was that they used either this or if the box history had sufficient number, they had some minimum that okay it has to be 20 or above. So if it is 20 or above, they use theta hat I, and if to estimate the probability, and if it was below 20, then they use theta, which is a sort of a sensible rule of thumb, but not very good compared to the Bayesian idea, which says okay we are going to combine. Let's combine them in the right proportion. So the right proportion is exactly in accordance with the weighted average of the precisions. Now the thing is that okay, this is known because that's the history for the whole. So we don't need to estimate this. Actually, what we are doing is we are estimating it based on all of the data, and based on all of the data, the estimate is quite accurate. So we can pretend that the estimate is the same as the true value. When we go to hierarchical Bayes, you will see that this makes a difference. But ultimately, when you look at the practice, you find that the Bayesian estimation does not make any difference when the sample size is very large, because the prior just washes out. It's just you have a very small weight that is attached. So anyway, this part is known. This part is known. The crucial thing that the Bayesian estimation does is to estimate this P, which is the prior variance. It tells you what is the P telling you? It tells you how much fluctuation there is in the boxes. So if in the neighborhood all of the boxes are very similar,
then you can confidently use the neighborhood average. So that means that basically if the P is very low, the precision is very high, the variance, the prior variance is very low, then you should use the neighborhood estimate. If on the other hand, the prior variance is high, each of the boxes in the neighborhood fluctuates a lot, some of them have very high probability of fire, others have very low probability, then the neighborhood estimate is not a reliable estimator for the individual box. So you should put more weight on the box history, but also there might be majburi, and if the box is empty, then the only thing you can do is to, so this gives you the exact optimal compromise that you need to make, and it's much better than just doing ad hoc, that okay, more than 20 we use the box and less than 20 we use the average. So basically what then they did was that they tested this on, they said okay, let's look at the data. They had exact data for the year, for many years, for number of fires and responses and so on. And they said okay, so if we use this methodology to estimate what would have happened, and so they found that they would get significantly more on target responses, that they would send an all out response to more genuine fires. Now, one thing very important to understand, which very often people miss, is that the overall improved performance doesn't mean improved performance in every case. Both procedures make mistakes, and you can even make mistakes of that the naive procedure, the one that you were using before, gets the correct answer, and the sophisticated empirical Bayes gets the wrong answer. And there will be some of those cases. So there are type 1 errors and type 2 errors. And very often people say that, look, if you, here is an example in which empirical Bayes failed to get the right answer and our old procedure was right, and therefore we should not make a change. So not one, you can find 5 or 50 such examples. The thing is that if there are 50 errors and there are 100 cases where empirical Bayes worked, then the net gain is 50, and that is what matters. So but you can say, and you can make arguments, and people do make arguments, and look, 50 cases show that this thing doesn't work very well, and our old procedure works much better. So by looking at counterexamples, like the example was given that nearly in every country that has developed, there has been universal literacy. So the more weight we put on primary education, the better it is for growth. So there is a counterexample to this. Ceylon has put a lot of money into education, but they didn't have a lot of growth. So people argued, when HEC was getting funding, then one of the arguments that was made against them, when Ataur Rahman was getting a lot of money for higher education, that actually that's not the priority area. Our priority should be primary education. So he said that, look, Ceylon is there, they put a lot of money in prior education, you have so much literacy, but you don't have growth. So this kind of argument is made often, but it's a fallacious argument, because when you have a probabilistic situation, there will be some type 1 errors and some type 2 errors, and if you just point to an example and say, look, this is the, so that example might be an exceptional case. And actually in Ceylon what happened was that they had a long-running civil war, which was the causing the prevention of development, and it didn't have to do with the failure of education. All right, so I think that's all for this. Yes, there is a lot of complicated detail which I have omitted, and as I said, you should go through it. It's not that and if I go through it, then I will remember it again, that okay, this is how it used to be, but it won't help you. But if you do it, then you will. So the next example is the example of the Bell telephone, which actually was implemented for quality control. And that's the last example for the simple cases where we basically have counting data. We are counting one thing and the other. And then the next section goes on to the more complicated case where we have continuous data and real economic type variables, where you have continuous and regression model type situations. And the third chapter deals with the hierarchical Bayes modeling, which is the most difficult. So okay, so let's stop this lecture here. Next time I will try to finish this with the quality control. One of my students actually did a thesis on implementing the quality control methodology. He was in the engineering department. He came to in Bill Kent, and he came to my stats class and then we studied the quality control method, and then he applied it in some engineering context. So these are all real world examples with real world implications and consequences. Okay, so that's all.